Okay, and so that was a bit of a clickbait. I guess that's a better title. So probably less people will come. Yeah, so it's I'm going to talk about something I don't fully understand, and it's about us trying to understand some observation we made empirically. And you know, if you find some better ideas to understand and rationalize, then it would be great. And yeah, I mean, a lot of clever people here, so it's a bit dramatic. I realize, you know, I'm slightly different from everyone else, because maybe because I'm a physicist. And it manifests in me using keynotes and not LaTeX Weaver. Apparently there is a law, but if you don't use LaTeX Weaver, you're not a mathematician. Okay, good. So why am I interested in this idea of Gaussian universality? Well, there is a good reason. It's that it gets harder and harder to understand, you know, these machine learning algorithms. There are things new every time. I mean, but these are things that, you know, they are new. Like 1 year ago, I did this stuff, and I had fun doing myself as Gandalf, as guitar player, or Obi-Wan Kenobi. And you know, we just recover from this stuff, and then you had bad stuff, which you all know. And you know, that's me exchanging some trivia with ChatGPT about who invented the central limit theorem, and apparently it's Laplace. Since I'm a French guy, I would remind everyone. And the point is that we are living at that time where this thing is happening, and can we do anything about this? Right? Can we even say anything useful? And it's kind of hard because these are amazing pieces of engineering, and you're not going to make a complete mathematical theory of this. So what are we all trying to do? So of course, one thing we are trying to do is to look at sample models and approximation and trying to build theories with tractable models, toyish models. So one of them, of course, is using Gaussian data. Okay, so Gaussian data is great, or should I say maybe Laplacian data? So yeah, I mean that's a great assumption because we can make a lot of computation. I mean it's already hard enough in many models to deal with Gaussian data. But that's why we do it, right? We try to make simplifications and look for things that we can solve. And Gaussian data is one of the things that we do. Now, when I say we do, it depends who you ask, right? So in the field I come from, which is statistical physics, everybody is doing this, right? There's no question to ask. In fact, when people started to do statistical physics and apply it, I mean, at the time people were doing neural network, but it was probably more motivated by actual brains than anything. And all the founding papers in this field, all the major ones, they use Gaussian data, the Hopfield paper, Gardner and Derrida, all these work by Hermes and Belinsky, and absolutely no problem. Let's use Gaussian data and try to do something. Now, of course, that's not only a physics thing. If you read paper in random matrix theory, I mean, those guys are crazy about universality of Gaussians. It's one of the major topics. Statistics to a point, it's also a place where you can do it. And some machine learning, you can do it. So you have a selection of paper, you have a paper, and then many papers, including some by many people in the room. All of this is based on computation with Gaussian data. Okay, so I see a lot of people here. Anyone can raise his hand or her hand if he or she never used Gaussian data in the paper? Hey, that's a lie. I know you. Okay, so apparently everybody is okay with that, right? Now, I hate to spoil it, but of course real data are not Gaussian, and you shouldn't do it, right? And if you take applied machine learning class and you learn to do something with Python, scikit-learn and everything, you're dealing with data sets like this one, cat versus dogs. These are not Gaussians. The celebrity data set, these are generated pictures by a guy, and it's not Gaussian. Even if you do the most basic thing, to be MNIST, not Gaussian. So real data are not Gaussian. And if you go to read statistical learning theory literature, people are really not happy with that kind of hypothesis, and rightly so. Okay? So the first time I was trying to be interested in this, I tried to open this book, and it's a hardcore thing, and you have to prove things. And all these Rademacher and DC bounds, they are trying to be data agnostic, and there is a good reason for this. But you don't know much about your data. If you want to have guarantees, you should not do this. Now, these two different theoretical culture clashes sometimes during referee reports in some conferences. So under anonymity, I will produce some of the comments by the reviewer too. Which, and I cannot tell which paper is using this thing. But, sometimes they let you know that they are not happy with this assumption. Now, of course, they are right. Okay, I mean, there is a good point of not making this assumption. It's a ridiculous assumption, which is not valid for any data. But we are also right somehow, because that's not why we do it. We are not doing Gaussian data because we feel we are close to truth. We are doing it as a toyish model to try to understand what's going on, right? And so, yeah, there is a philosophical debate: what has value, what has no value, which is interesting.
So Florent, reviewer 1 was fine with Gaussian data?
Yeah. It's always too. I mean, I've been told, right? So, yeah, I mean, so, fair enough. Now, the thing is it true, actually, that real data are not Gaussian? Because we're working with really high-dimensional systems these days, and and you might hope that some CLT behavior kicks in. And it's so obvious that you never have anything close to Gaussian with real data. I don't think it's that obvious. And so that's part one. Okay, so real data are not Gaussian, or are they? So I'm going to show you two sets of numerical experiments that we did over the last few years. So, and I'm going to restrict myself to a very simple architecture of learning, just a two-layer network with fixed weight at the first layer, right? And most of the time they will be random, so it's usually called the random feature model. And I'm going to learn only the second layer. Okay, and so why doing this? Because deep networks are hard. Also because it's not such a bad method. Actually rather good. It's not excellent, but it's rather good. And if you take a large intermediate layer here, this is equivalent to the kernel method. The kernel method are great, so it's good. And over the last few years, there have been a renewal of interest following all these ideas that even if you have a deep neural network, in some regime, it's called usually the lazy regime, or the fancy name, the neural tangent kernel. In some regime, even those guys behave like a two-layer model with fixed features. So of course, it's a limited, very limited setting, but if we don't understand this, we're not going to go beyond. That's what I'm going to look at. Okay, so experiment number 1. Gauss versus dumb nature. All right, so these are Gaussian noise, and these are data from Cypher 10, I believe. So here's what the experiment is. I'm going to try to fit a Gaussian model to this data set, learning the mean. I mean, actually, I'm going to remove the I'm learning the covariance, so covariance matrix, and then I'm going to have a Gaussian theory, like you can do, and I'm going to compare this theory to simulations in terms of training error and generalization error. Okay, so how do you do this? Well, for the data, you can just fit the two moments. For the label, you have to work a bit more. So here is what we did. It's a construction that we took from Chinese. Right? So we took it from him. So here is what we do. You have your data. You first have a random feature that goes into the very large space. And we take it really large so that we can fit all data perfectly. Okay? And then we send this data to another random feature map, the one we are using to classify. And here we are fitting the function that is perfectly reproducing all the data in the dataset. Okay, so it's cheating because we are fitting the dataset, but that's the best way I found to have a Gaussian theorem. Okay, so the good news is that once you have that kind of construction, you fit the label, then you complete the correlation matrix between all these two sets of vectors. Everything that, if you assume that this was a Gaussian vector, you can write a theory. You can do it with replica if you want. And if you work hard, you can prove it, because we learn from you guys how to prove stuff. And since we are using just optimization of second layer, this is not so hard. We can do the Gaussian Mi theorem. So that's how it looks. It's not really important, but if you have two vectors that are correlated this way, and the label is coming from that vector, and what you're fitting is coming from this vector, the generalization level is given by this formula, training on this formula in the large dimensional limit when the dimension is the number of data goes with you. Okay? There's a formula, you can solve it. You just have to minimize this 6-dimensional formula and compute these 2-dimensional tables. It's not so hard. Anyway, so that's great. We have a formula, so how it looks. Okay, so Gauss versus reality. And here are a set of experiments on the MNIST, right? But the number of samples. And this is what is going on with different choice of the first layer. No first layer or identity. Random features. We use even some kind of fancy thing, like the scattering transform of Mala and Bruna, or some kernel, I don't remember which one, probably the Gaussian kernel. And that's the test error, and this is a training error. And the lines are the result of the Gaussian theory, and the point are the simulation. So, looks very, very nice to me. In fact, everything seems to agree quite well. So, the Gaussian theory doesn't seem completely off. And it seems to agree quite well with reality. And there are other examples by Chengiz using kernel and observing like that.
So, Florent, just a quick question. So here you do ridge regression. How do
it's
you?
ridge, yeah.
So you do just the quadratic laws on 0-1 class.
Yeah, and
how
I
do you select
probably
lambda?
select
By cross-validation?
Not sure. I think choose one.
You just fixed, okay.
We have more points like this, but yes, it's just ridge. That's a good point to remember that this is ridge. This is also ridge on another data set. Here we have a lot of fun because what we did before doing all this construction, we even learned, so we had an ordered set, we learned the first layer and we pre-trained it on some data, and we kind of learn some features. And so depending on how much you do pre-training, when you learn with a new set of data and just learn the second coefficient, you have that kind of agreement, which is still okay-ish. I mean, remember that this is a Gaussian construction that is supposedly working at infinite dimension, and without data in finite dimension, so it's not so bad. Interestingly, if we do logistic loss or something like supervector machines, it's not as good. I mean, it's actually quite crap, as you can see. Okay? So, and there are good reasons for this. If you think a bit about it, once you start to use these classifiers which try to do some max margin construction, they are probably a little bit more looking into the geometry of data, and so approximating everyone as a big Gaussian is not a good idea. So, that's interesting. So Gaussian theory kind of works quite well with real data for the ridge loss, and much less for over loss. That's an observation that can be made. Okay, second set of experiments. I don't like this construction of trying to fit the real labels. It's too complicated. So let's use random labels. Okay, so you may say, why is random label interesting? Well, there are many reasons why it's interesting. That's how you construct, for instance, the BC dimension, the Rademacher complexity, and all those things. So it's interesting to see how something fits a random label. So here I'm doing the same experiment. A real data set or a Gaussian data set with matching means and covariance, trying to fit them, except that for each data point I use a random plus or minus 1 value. And I compare the analytic theory, and and simulations. Okay, and again, random label. So now, that was the thing that really surprised me. If you use random label, and this is for the Hinge laws, the logistic laws, the Hinge laws for different value of regularization, when you ask for value. And you know, Gaussian theory is really basic. And, that was really something. I mean, I thought my student made a mistake and plot twice the same thing. I could not believe that was agreeing that much. And so that is one of the things. I mean, I wanted to understand this. Why is it working so well with random labels?
But the real data also has random labels.
The real data also have random labels. Okay. So before I was trying to kind of fit the teacher, and it was okay-ish, at least for regim. But now it's quite good. So this is MNIST with Gaussian random feature, fashion MNIST with wavelet scattering, Cypher10 with Gaussian random feature, and these are actually Gaussian mixture. Gaussian mixture are not Gaussians. Okay? And everything was working. So I still don't understand the stuff, and what I'm going to tell you is what we managed to understand by training.
Florent, just
Yeah.
so what is the Gaussian curves are derived under assumption x and y are jointly Gaussian?
Y is just plus or minus 1, so whatever independent.
So only the features are random Gaussian?
Yes.
Okay, and then y is generated through what? Through anything? Also,
And the pickup random.
so the only assumption in the Gaussian theory is the px?
Yes.
Okay.
Of course it's simpler. You expect this to be better than the one where Y is correlated. But still, I mean, I would not expect it to be better. Something even better, if I send lambda to 0, you know, so in the limit of interpolators, all these curves go to a single curve. I don't even have to fit anything. Okay, it's the master curve for, this is for Hinge and this is the logistic class. Okay, and so that's also an extremely good agreement. And yeah, I was puzzled by this and I'm still am. So we are trying to understand why this is. Okay. Obviously, you know, you would say, oh well, you know, it's in high dimension, there is some random things going on, and there is a concentration. Yeah, I mean something like this is going on, but exactly, I don't know. Okay, so here is part 1, you know, and we did some experiment, and for linear model Gaussian theory, at least in high dimension, is often close to given data, at least for range, and with random labels, it's, you know, really, really.
I mean, I feel like maybe there is at least some kind of intuition for this, right?
I
Like,
hope so.
okay.
But if you are getting it now, you are studying everything that it says.
It's a great way to answer the question.
Give me some rope, man. Yeah, I mean, you know, but okay, let me tell you what we try to do and what we got, and when it works and it doesn't work. Okay, so the first thing we try to do is to say, okay, you know, what is a better model than a single Gaussian? Of course, the answer is 2 Gaussians, and 3 Gaussians. And I mean, you know, if you have many Gaussians, if you have a Gaussian mixture, you know, it's an universal approximator, you can approximate any densities. Gaussian mixture is a rather good one. So let's try to study Gaussian mixtures. And so the question is, okay, so if the data are a Gaussian mixture and I send them to a 2-layer neural net with fixed first layer, what is going on? So that's not too hard to find out. You know, you can make a Gaussian mixture theory. One thing which is important is there is a universality of Gaussian mixture in some sense that I'm going to describe now. It's a generalization of essentially a work by Liwei and student and also by Freya. It's rather trivial generalization, but we need it. So let's say that you have some Gaussian mixture. You send them through a frost layer with, you know, random coefficients, and the dimension here and the dimension here is commensurable, and they all go to infinity. So these are your data after one layer. Oops, sorry. And now you train the second layer, and with convex loss with convex generalization. And what you can show essentially is that in the high dimensional limit, everything is as is. Those data were themselves Gaussian mixture. Okay, not completely trivial. You need to work a bit, but that is a bit slightly intuitive. They are not Gaussian mixture, okay? But if you train them with a linear model, basically you feel only the statistics that is captured by Gaussian model. Okay, and the condition that you need to have, you want to prove that, you need to show, you need to have that matrix here is, well, the random matrix is fine, or random orthogonal matrix is fine, or even deterministic condition that you have some orthogonality conditions.
Is there any condition on the number of mixtures?
Good point. Yeah, it's finite, which is kind of bad for right? That would be.
No.
Yes, yeah. I think one should be a little bit more careful here, because, for instance, if the true vector theta is aligned with one coordinate axis, then this is definitely false. Also,
yes, they are continuous.
this is generically true. Okay, false.
Yes, all right. I agree. One is
Some slack.
Okay, but that's
Yeah.
mostly what's right. Yeah, there are many caveats. Yeah, so that's all I'm going to need here. This thing, so just hardcore stuff, this fantastic papers about doing the case of one Gaussian, multi-Gaussian, very trivial. That's not why we did it. So let me skip the sketch of proof. There are many things that I don't know about this. Jai is mentioning one. One which is a bit annoying is the fact that I believe it's true even if you have a multi-layer generative model from the physics. I don't think anyone managed to prove this. But numerically it works perfectly, so it's probably true. And another thing which is open, and I would tend to think that this is actually wrong, is does this thing still works if this guy is very large? Like if D, small d is, big D is D squared with respect to D. So there have been a lot of works, especially Timo von Leer and Theodore and some May. And very recently there is a fantastic paper by Theodore and Yue and Pennington, when they show that you have some universality for kernels, but it's a universality for the spectrum, which is not as strong as the kind of thing. But okay, so these are important open questions, but let's forget about this. Why is it interesting? Well, I'm trying to sell this, tell you that Gaussian mixture, even if a finite number of mixtures, is probably a good model to test these ideas of universality. So here is generic picture. So think of a generative neural network, nobody is doing this anymore because everyone moved to score-based diffusion and everything, but okay, let's pretend that we are 2 years ago and that was the state of the art. You start, one way to do this thing is the DC GAN, the conditional GAN. For different categories, you start with a different Gaussian. You send them for a network that you have learned, not a random one, and then you generate nice data. Okay? And so that was the way that many people used to do data, and kind of cool, right? That was the kind of thing you can do. If you're interested in generating burger, mushrooms, and pizza, certainly would do the trick. And so, I use this as a proxy of real data. So here is the chain of thought. So let's say that you have a latent space with Gaussian data, Gaussian mixture. You send them from the generative model. When you are learning, all the weights are learned hard to generate something cool. And then you use a frequency model to predict what's going on. And you learn only the last figure. Okay? So I claim that obviously, you can just do as if those Gaussian here, those data here are Gaussians. Okay, obviously this is wrong. At least nothing here is covered by any proof because I'm learning this thing, it's multi-layer, And in fact, you can see that this cannot be true, and when you run it, it's not true. However, if you are using random feature as the last layer, it's not quite bad. It's quite, it's quite good. Even though nothing is covered by a theorem, if you compare what's going on by just fitting these random features, assuming everything is a Gaussian mixture and replacing real data by Gaussian mixture, you don't see any difference in train loss and testing classification between the two models. So my point is not completely crazy, at least from this point of view, to think that once you look at some data set, they kind of look like, for this model, like finite number of mixture. Maybe you don't need to have a huge amount of mixture to approximate reality. That's something I don't know how to quantify, but I'm going to harvest. Okay, so there are two takeaways from this. So the first one is, okay, Gaussian mixture, I try to convince you they are a good model of real data, at least if you use fixed feature and randomish fixed feature. And there are a lot of things to be understand about this Gaussian universality theorems, which is not the main topic of okay. So now that you are all persuaded that Gaussian mixture is a good model, let's come back to our first topic. Okay, the first topic was, okay, how come real models look like one Gaussian? Okay, so Ankur understood already why. For the rest of us, let's try to come back to Gaussian. So what I will try to study is the following. Okay, so if I replace one Gaussian by a mixture of Gaussian, do I get different numbers? And that I can do in theory, that I can compute. Okay? So I can compare a model in which I have a mixture of Gaussians, then replace all of them at one Gaussian. Of course, I need less covariance to match the entire covariance of this data, right? But it's certainly a big simplification. Okay? And so that's what we can do. That's what we can do very easily. Very easily. Requires some knowledge. And of course, we do this after observing then a random feature model. But it's basically the same as not having any random features, and because mixture of Gaussians are mixture of Gaussians. Yeah. So the cool thing is, it's basically just looking at in high dimension what happens if you do a linear model to a Gaussian mixture versus if you do a linear model to one Gaussian. Okay, so that's what we try to look at, how different they are in high dimension in terms of training error and generalization. Right? And of course they should be different because these are very different. Okay, so in order to do this, we need the asymptotic error for a Gaussian model that we have. Many work over the last 10-15 years. We also need the asymptotic error for the Gaussian mixture model. And so that's something on which we work quite a lot. I mean, in Physicists, we first did it with replica, so assuming the model is something like this, trying to derive the free energy, the generalization error, training error, blah, blah, blah. We did it with replica. Then we try hard to prove it. Turns out that was not easy, at least for us. And we did it with approximation such passing technique. It was a very kind of clever construction where we transform this into some kind of specially coupled set of matrices, and then you have to prove anything for that. But it can be done, and you can prove all these results, at least for convex fields. Okay, so good news is that.
One question from
yeah.
here. Theta naught is, what is the relation between theta naught and the centers of the Gaussians?
Good point. So keep this in mind. There is a theta naught. Okay, so let's say that for this model, you have this, but I mean, everything works with deterministic theta naught here in terms of formula. Yeah. Now the question is, of course, what is going on with what theta naught does? And I agree, that's a very important question. In fact, if you look at this slide, you see that I'm introducing this thing, which is angle. Let's say that, let's consider the case where there are two homogeneous Gaussians. Okay, and if you want to be fancy, you call them heteroscedastic Gaussians. One case is this one. and one case is this one. And of course, in high dimension, if you pick up a random direction, it will be like that. But if you want to be adversarial, and I suspect that's what you have in mind, you could figure out, what if I do a direction like this one? Obviously, you expect things to be different. And indeed, that will play an important role in that. Okay, so the formula is what it is. It depends on that. But the reduction to Gaussian is drastically dependent on the teacher. So let's see what happens. Okay, so anyway, that's the kind of replica formula that you have. And by the way, they are awful. I spent a lot of time integrating replica formula, but that was one of the cases where I didn't want to integrate. So it was actually harder to analytically try to see if they have any relation with the simpler Gaussian formula. That's what we did. But that's what it looks like, and you can see that it's more involved than in terms of order parameter. You have one by Gaussian mixture, because you start to have the order parameter is how much your predictors, the theta hat that you're learning is correlating with the centroid of each Gaussians. So of course I can do this only with finite number of Gaussians. I need to prove what refer to rewards only like that. And I could not even solve them. So it's all finite number of Gaussians. That's all I can do, and I'm going to do better. So anyway, let's look at one example, and this is probably what Andrea already understood half an hour ago. So this is the angle, okay, which is here, okay, in x. And that is training generalization loss. It's a training loss. So it's a training loss predicted by the theory. So the red line is the Gaussian mixture theory, and you see that the error you get depends a lot on how your function is correlated with the data. And same for logistic loss. What is interesting is to plot what would be the Gaussian theory here. Now, of course, in the Gaussian theory, there is no such angle, because all this guy is a bubble. You might say, oh, there is one direction. Yeah, it's one direction. It doesn't make any difference in one dimension. And so that's what would be the one Gaussian theory. Now, there is something interesting still. Oops. Which is the fact that when I have a strong correlation, so that guy, okay, and here that means that the task is really, really correlated with the data, okay? And in that case, you see that the Gaussian theory is completely bad. And probably it's actually the more relevant case. The work of Andrea when he studied the advantage of kernel versus neural network in similar situations. So here, they are not universal. Interestingly, I have no idea how this thing works. Yeah, like this. If there is no correlation at all, if you pick up a random direction for the teacher, well, essentially, you have no difference with Gaussian data. So once you observe that was done by integrating the formula. You think, okay, maybe I can try to see if I can show this. But first, here is the summary of running these two evaluations. When the data structure is not correlated with the task, single Gaussian seems to be very good. The same as the Gaussian mixture. And you can run this with 5 mixtures. It seems to be always the case. One thing which is interesting is the numbers here. Like here you have 0.096 and 0.108. These are very close numbers. So even if it is not the same, it's not the same. If you do this on real data with finite size, it's hard to tell the difference. For logistic loss, we go from 42 to 36. It's much sizable. Okay, so already this is telling us that for ridge loss, the ridge is not, the ridge is a bit an imbecile. It's not enough clever to feel things, and so it's missing. You can see the difference, but maybe that's why I could not see it. That's the first thing. And the second thing is, okay, there is this thing, when you are not correlated, when the task is not correlated, then you seem to have a strong universality. So we try to see if we could prove this, and so to do this, you have to take the replica formula for one Gaussian, the replica formula for many Gaussians, and you can try to prove that if you plug the solution of this one to the other one, it's also a solution. And if you have proven that there is a unique solution, then very cool. And okay, that's kind of what we did, and we tried to play this game. Okay, and so I'm going to show you 3 theorems, and they're all a little bit different. So this is where, if you think, oh yeah, it's trivial, well, there are some interesting effects, which I still don't fully understand. So here is theorem number 1. Assume an almost cadastic Gaussian mixture. Okay, and so I really need, you have 5 Gaussians, and they all have the same covariance. Now, assume the labels are uncorrelated with the structure, so random teacher, the easy case. Then you can do the work, and you can show that when n and d is going to infinity, and alpha and innovative fixed, then the 2 error, the error of Gaussian mixture for a finite number of mixture, it would be interesting to get some weights in this price, because the same one has a single Gaussian, so you can show that there is universality. So I thought that was interesting, and I was not completely expecting this. And somehow for me it kind of explained a bit what we see best. Now of course there is no reason why MNIST and fashion MNIST or CIFAR would look like heteroscedastic Gaussian mixture. Gaussian mixture certainly now I understand this. And here, well, one thing you can see from simulation is if you look at the covariance after a random projection, you look at the covariances of the different data, you look at the covariances for, let's say, the cats and for the dogs, they kind of look similar. And it kind of makes sense that a random projection is kind of homogenizing everyone. And in fact, you will see some effect. But, the wavelet scattering is a little bit more fancy, but for me, that was the best I could do to understand this picture, at least, the fact that I can show this. But it's interesting because if you look at the literature, there are many papers where people just derive things with Gaussians, and well, you can replace Gaussians by a mixture of heteroscedastic, almost scedastic, sorry, Gaussians, and it still works. So, for instance, the work of Praga with Emmanuel, when they had the phase transition of the maximum likelihood estimator with logistic loss. That was done on Gaussian data with a random teacher. And so this line is really universal. You got the same line for a large amount of data. Anything that looks like a Gaussian mixture and which is sufficiently homogeneous will have exactly the same transition. That I was not expecting. You can have the same kind of fun with orthogonal projection and random features, and you also can see that you have some interesting universality. For instance, here, okay, I'm showing what happens with Hinge and Logistic with different data sets. So MNIST, fashion MNIST, CIFAR 10 after random projection, and compare with Gaussian theory. And the phase transition, of course, is as 1, but training loss is always the same. This is as lambda equal to 0, so this is really the constant, and this is a separability transition. You can see again that they all arise at the same point that we are computed. So that I think is cool. And then, in some ways, if you say, oh, this is not interesting because it's just Gaussian, well, it's a bit unfair, because in reality, it works quite well with many data sets. Okay, so then we try to see what we could do. If you don't like the almost cadastic Gaussian mixture, let's try to do something else. So, reach, interpolation, so lambda is going to 0, to 0 plus, really the misnorm interpolator, and random labels. Okay, and now the point is we can assume a general Gaussian mixture, still finite, but it can be heteroscedastic, so now it's really, really much more permissive. Then you massage the equation. It was a little bit more tricky because the replica formula, you have things which are, each of them is diagonal in the basis of each covariances, so it was great. Now suddenly you cannot do this because they are heteroscedastic. But the miracle is occurring at lambda equal to 0 and with random labels, and so you work hard. And this is what you get for ridge with random label. A mixture of Gaussian, any finite mixture of Gaussians in high dimension is giving me as the training error 1/2 of 1 minus 1 over alpha, okay, which is the result for Gaussians. That's cool, and it's certainly stronger. Of course, the plus or minus 1 label condition is extremely strong, but yeah, still interesting. And so that's this plot. We show you, right? This is the slide. And and it works quite well. We try overlay at some mini ImageNet, and it works really, really well. So now I think at least the rich part, for me, that's the best I could do to understand this stuff. Okay, and now in all of this, in these two theorems, there was a catch, and the catch was the first one. I used a random teacher. So, it was not correlated with the data. And of course, it helps, right? I mean, you expect that if the task is not correlated with the structure of the data, maybe you are less sensitive to the structure of the data. Okay. And the second theorem was also about plus or minus 1 label, which, again, you are not really sensitive to the structure of the data. But still, that's interesting. So let's try to see if we can do with arbitrary linear teachers. So not arbitrary labels, but, arbitrary teacher with arbitrary angles. So that's a little bit more interesting. And in this case, there is one case where we can show something. So again, large dimension, alpha fixed, ridge regression with this norm interpolations. And now for any choice of the mixture, the training error is universally given by delta, which is noise here, times alpha minus 1 over alpha. And this is for alpha larger than 1. And if, and only if, the mixture is almost elastic, the generalization error is also universal, and divided by essentially the same formula. Alpha 1 over alpha in differential. Okay, so why is this interesting? Well, it's interesting because now you can try to look at interesting phenomenon. So look at the first one. Let's use random features. So I kind of ask that if you are using random features, you reach almost elastic data, right? Because if there was some direction, you're kind of mixing them. And now let's look at the training error. So again, fashion MNIST, CIFAR, but we're using a random direction. And any direction. We try many of them, doesn't change. And here is what we have. The training error, well, of course, you have 0 before 1, because you can fit everything. And then you have this universal curve, which is different from the previous one, but, because before it was plus or minus 1, but it is universal. Now, what about the generalization? So if you come back here, you see that the generalization is universally given for alpha larger than 1. And indeed, it works well. Okay, and that will be the kind of plot that were derived for Gaussian data by Andrea and Sondheim for random features, and they work quite well. But you see, it doesn't work here, right? And it's not a problem of the proof and the identification of the two replica formula. They are different. The generalization is different. It depends on the data set. Okay, and what is interesting is that if you move from random feature map to deterministic feature map, we tried raw data or wavelet scattering or even some orthogonal projection. And if you look then, like the covariances matrix of each subset of data, so restricted to the 1, to the 2, and you can see there are still retain some structure. And so the data are not almost stochastic. And what do you see? Well, training loss doesn't care, because they didn't need this assumption. But now, even at alpha larger than 1, you can see that the data don't look close to the Gaussian theory. All right, so basically that's what we have. And we try to build these equivalent classes. I mean, the takeaway, well, I'm trying to argue that the Gaussian mixture is a good model. And with some assumption that at least we could identify in some cases, simple Gaussian works well. And I like this because my school of thought or my colleagues in physics have been working with Gaussian data for 40 years precisely in these conditions. And I've been told by people in statistical learning that you should never do this, and it turns out maybe not such a stupid idea. And, I think it's nice that all this work that on Gaussian data seems to be a little bit more generic. Okay, so let me finish with a set of questions. So, can we understand this universality and their limit more fundamentally? I don't like what I did because I don't understand. Okay, I mean, it's one thing to write a formula with one Gaussian, a formula with many Gaussian, and to say, haha, look, they give the same thing. But it's not that I understand what is going on in terms of geometry or in terms of probabilistic models. So someone more clever than me can probably figure out stronger condition and maybe more intuitive. Another thing is, of course, this was for random features. Okay? Very limited models. So I'm not claiming that anything will be as Gaussian. In fact, you can see this, there are two ways you can see this. One way is to say, haha, it's cool, Gaussians are great, which I agree. Another way you can say, aha, random features are completely dumb, because they are not able to see more than essentially the first two moments from this. And this is true. If you are not using random feature, you will see things which are not Gaussian. I really like this experiment that was done by Sebastian Gold in ACTP. So, he took cipher 10 and he created the Gaussian equivalent. So, replacing every data with Gaussian data. Then he trained a neural network on the Gaussian equivalent. And that's the generalization you get. And this is the one which has the real data. Right? And what is cool is that at first, they kind of give the same thing. And then you realize that the neural net is clever enough to pick up that, okay, this is not Gaussian noise. Okay, and it's interesting, actually. He also tried the Wasserstein-Gann model, and you can see that the Wasserstein-Gann model also gives the same result, but it captures much more behavior of the data. But even trained on this data, at some point you realize that training on real data gives you better performance, right? And so it's kind of cool, and it tells you that maybe there is a hierarchy of moments that you can learn, or by polynomial or something. I kind of like this plot, whatever it is. Okay, so many things more can be said in this topic, including some interesting properties on kernels and the fact that Gaussian exponents seems to be the same as the worst case for some kernels, and we also have something on the random convolutional design by Max Daniels, who is somewhere here, and is working now with Philippe, so if you want to know this, you ask him. And I'm moving to the end. These are the papers used. Look at them if you're interested. And I thank you everyone involved into this, and especially Laplace and Gauss for helping me figuring out the stuff. And I leave the last one for questions.